I'm Dennis Garrity, and I'll be your moderator for today's session. I have the distinct pleasure of introducing Mr. Oswald Petersen to share with us an update of his work in developing removal methods for methane from the global atmosphere. He'll be discussing the method that his team has been developing, which they project could remove large quantities of methane during the coming years with modest investment levels. Oswald is CEO of the company Atmospheric Methane Removal and is based in Germany. He's an active member of the HPAC and a member of our advocacy task force as well. He's a German economist and IT consultant who graduated with a diploma in national economy from Free Universität Berlin in 1989. And he has continued to live and work in Germany, Australia, and now Switzerland. His professional focus has been on the IT of the health industry, but in 2008, he worked with Renaud de Richter on solar updraft towers. And in 2020, he became a member of the initiative Restore Our Climate, where he has learned about iron salt aerosols. In 2021, he founded the company, Atmospheric Methane Removal, and his objective is to find technical solutions to cool the planet by enhancing natural forces. So he'll share his remarks with us for about 20 minutes or so, and then we will subsequently have an open discussion on the topic by HPAC members attending today. So Oswald, a very warm welcome, and the floor is yours.
Oh, thanks a lot, Dennis, for this wonderful introduction, and thanks for having me in this great group, HPAC, which is the third group, actually, I attend, doing very much the same, learning from scientists, which is an absolute pleasure. Do you see my screen?
Yes.
Very good. All set. You can put it into presentation mode, however.
That's right. Exactly what I'm trying to do.
Little screen on the bottom right of the of your screen there. But if you have trouble, you could just leave it and carry on. It's quite readable.
Is it okay like that? Because I can't get it to. Normally,
yes, sometimes it is a problem, but it's quite fine to leave it like that if necessary.
Okay. Right. I wonder if I can get rid of this. That's better. All right. The GeoRestoration Action Plan is, or what we call GRAP, is going to be our subject here. And I've tried to move everything away. I don't know how well you are acquainted with this, but I will basically show you the introduction that we give to potential investors, assuming that you know the basics of climate science. I think I can assume this in this round. So I don't have to start from the beginning. Yes. But it is quite important to start from the theoretical point of view, what we call georestoration. It is very important for me because I've basically formed that term to define what we are doing. And it is something that has occurred to me quite often, is the fact that our method is a geoengineering method, and geoengineering has a very bad reputation. And therefore, I'm trying to coin a new word called georestoration, which is a subset of geoengineering methods, but only certain methods can qualify to be called georestoration, and that's all those methods which do have a program of restoration, which means roll back to the old climate. And georestoration includes atmospheric methane removal, enhanced weathering, marine cloud brightening, and ocean iron fertilization, because these methods, in all their different ways, and there's more, this is not a complete list, do actually roll back the climate or aim at rolling back the climate. And not all geoengineering methods do that. And for us, georestoration is a safer way to do things with the climate than the general geoengineering term. Basically, what we are saying is the only power in this globe that can actually restore the climate is nature. And man's engineering is always way, way, way too weak. Very good examples, DAC, the idea to run the complete atmosphere through a man-made ventilator is so ridiculous that I can only laugh about it. But many people really think that is possible, and it's not possible. The only power that can actually restore the climate is nature. And nature, again, can be triggered to behave well and do what we want her to do, but we cannot master her. We cannot tell nature what to do. We can only serve nature to her best. That's a very distinct and, for me, very important distinction between georestoration and geoengineering. Okay, that's all the theory. All done. Now the fun part starts. The action plan. We want to disperse FeCO3 particles from small planes flying at 2,000 or 4,000 meters over iron-poor subtropic oceans. So that's, in one sentence, the whole plan. And why do we want to do that? Because it has three impacts. The main one has been mentioned by Dennis. It's iron-3 chloride, quite known fact is that this material is a natural catalyst which removes methane and ozone from the air. Then the second one is ocean iron fertilization. I need not explain in this round what that is. And the third is that these particles serve as cloud condensation nuclei, CCN, which helps clouds to form. Now, again, a bit of hard work, facts and figures. I know Robert Chris loves figures, so he would be delighted to see this. Our goal is to remove 300 megatons of methane per year to reduce the methane levels from 1.9 ppm to 0.7 ppm within 20 years. We will use 40 to 60 planes or drones at full capacity in 8 locations for these 20 years at full capacity, and then another 80 years at half capacity. You know the molar weight of methane is 16 grams, the molar weight of FeCO3 is 160 grams. That's very good because it's very easy to calculate. We reckon that we can do 10,000 catalytic cycles per 1 FeCO3 molecule. That is based on the fact that we think that these particles will remain in the atmosphere for around 3 weeks. And since we know from literature that the catalytic rate is 80 catalytic cycles per hour, we can assume that we will get 10,000 catalytic cycles. It might also be 20,000, it might also be 8,000, somewhere there. But the average is going to be in that region. So that gives us 300 megatons times 10, because we have the molar weight to reckon the molar weight. And then we divide that times 10,000. So we get 300,000 tons of ISA or FeCO3 over 20 years. That's what we have to emit. Now, 1 ton of methane is equivalent to 12 tons of CO2. That's a long, long story that's behind that. There's GWP involved and many different figures, but we have decided that we are not going to go with GWP, but we are going to go with GTP, that's global temperature increase potential, rather than GWP, and that gives us 12 tons of CO2 per ton of methane. Now, if we have 300 megatons, that equals around 3.6 gigatons of CO2 with this measure at a cost of $2 billion. The cost per ton of CO2 equivalent is around $0.66. Okay. Now, all these figures can be discussed at length, but we will go on. Look at the locations. This is the wonderful, beautiful locations where all our staff will reside when we are this million company that will run all these planes. Beautiful places. I would make a pilot license if I wasn't too old for it. Okay. Then we will look at atmospheric methane oxidation, or AMO. That's the main focus we have been looking at. Out of the three effects I described, this is the main one. The catalytic effect of FeCO3 has been described by our co-founders, Franz Oest and Renaud de Richter. The process is 100% natural, energized by sun and wind, happening since millions of years. So this is why we can say this is a natural process. And the efficiency of the dispersion driven by particle size, location, and altitude of output, these are the most important parameters for the efficiency. And with the dispersion technology that we have developed in the last 1.5 years, these particles remain airborne for around 4 weeks and travel 7,000 kilometers. Okay, I did say before it's 3 weeks, but sometimes we say 4 weeks. It always depends a bit on how you calculate, but it also depends on wind speed, so it will be different every day. Now, we don't only rely on books, but we also check the science in our lab. Today, for example, I was in the lab, and I actually was able today to get the methane level in the lab down from 2.4, that was what I found, to 1.35 in our lab. So it actually does work, and we do check these things in a lab ourselves. It's not all theory we rely on. Okay, and we also found that we can generate FeCO3 nanoparticles. That's one essential part of our theory, is that you use nanoparticles, very small particles, because only nanoparticles remain airborne long enough. If the particles are too large, they will sink. Everybody knows particles always sink, and these also sink, but they sink very slowly. And if we have enough height to start from, and with the plane, we can actually decide which height. We can choose the height for every day. We can choose another height depending on wind speed and weather conditions. So we can always be quite assured that we can really make those particles remain airborne for 4 weeks, which is really important for us. And the methane concentration in the air can be reduced from 2.2 to 1.4. Actually, today I did 1.35 to celebrate. It was a record day. 1.35 ppm mixing FeCO3 particles under the influence of UV light. So we can actually show that in our lab. All right, okay, that's why we think we are ready to do a field test this year or next year. And that field test we want to do with this drone, probably. It's not quite sure yet, but probably we want to use this drone. We just have to find the $300,000 that it costs. But I think we will, and then we will have this drone, and it can go up to 8,000 meters in fact, but we only wanted to go up to 2,000 meters within 1.5 minutes and remain airborne for 15 minutes. And our field test will only be 10 minutes. So this drone will bring us to that height, and then we can run our disperser, which we are actually currently building. Then we can have our field test. However, that will only be around 500 grams of FeCO3, and that's of course not enough to cool the climate. Therefore, later we will have a larger plane, but not a very big one. This is probably the plane we will use, and we will use it in an unmanned version. So at this stage, it's only available with pilot, but we will use it, and we will develop with that Polish firm. We will develop an unmanned version of that plane, because there's no, I mean, we fly all these eight-shaped courses, very boring business for pilots. So actually, we will not have it. We will just use it as a drone. Now, the cost is around $1.3 billion per year. Well, that's a lot of money, but then again, if you can cool the climate by 0.5 degrees, which is our goal, 0.5 or even more, then $2 billion is actually peanuts, to be honest, in comparison to all other ventures we know who try to cool the climate. Okay, our income will be exactly the same, because our income will be cost-driven. We are not aiming at making large profits. And also, we just decided that we will not enter the negative emissions market. And on the negative emissions market, we could probably theoretically have a huge profit, because 1 ton of CO2 equivalent, which costs us 66 cents, is currently, you can sell that currently at $40. So that would be a nice profit. However, we will not enter the negative emissions market. Or it's a very simple reason. The quantity that we would offer on that market would basically destroy that market, because the market is very, very small. If you come and try to sell these quantities, then the market will virtually disappear, because nobody else can compete with these prices. And we do want other initiatives to keep going, and we think that they are all worth it, and therefore we will not enter the negative emissions market. That means we have no income, but $2 billion is so little per year that we think it will not be our biggest problem to finance this. Now, just a word about us. We are this team. Actually, this is only 6 out of 40 shareholders, but most shareholders are quite passive. So I think 10 are active, the 6 most active ones you can see here. And you know Renault and me and France, so you know 3 of us, and there's 3 youngsters as well. And we are a thriving company, but we have too little money, so we are looking for money. That's one small problem we have. But that is all solvable, and we are very optimistic that this will actually happen within the next years. Also, one word about caution. We do adhere to this EU precautionary principle, because this principle, and I like this text very much, is it includes a risk evaluation and an evaluation of the potential consequences of inaction. And that is something that I really always say when people say, oh, that's very risky you do. And I always say, well, it's also very risky if we don't do this. It's also very risky to be passive with regards to the climate crisis. Okay, that's my little introduction. Hope you had some fun here, and if there are questions, please go ahead and fire away. Shall I stop this?
Yes, yes. Thank you so much, Oswald, for that brief but very informative summary of the work that you and the company are doing. Very, very useful. I must say I was amused to follow the very animated email discussion during the past week or so following the announcement of this session. And so I'm quite confident we'll have a lot to discuss today in relation to your remarks. Perhaps I could start things off just to ask you a little bit about the current directions that you're following to deal with the permitting challenges that undoubtedly will be coming up as you operationalize this. How is that going?
Well, I must admit we didn't really look too much only on a very theoretical level at permits. We are currently preparing an EIA, that's an environmental impact assessment, for our first field test. So it's all very small at this stage, but even for a field test, you are required to make an EIA. So that will give us the first contact with permits. Up to now, we really thought about technology and economics, and permits were something in the future. And it still is a bit like that, but it's coming closer now. And yes, we will then talk about that in half a year when we are coming close to that field test. It's one thing that is not decided at this point is the location of the field test. And for the permit, it is very relevant where you do the field test, because of course it's the country where you start that decides if you can do this or not. And law is quite different in different locations. So we are looking at the American version of an EIA because that's very known and it's a very good standard. However, it doesn't necessarily mean that we will actually do the field test in the United States. But we think that it might be a good idea to use that as a standard. Okay. And that's only the field test. The actual permit for commercial use is 2 years away from here. And no, I can't really tell you more than you know yourself about this situation.
All right, very, very good. I would encourage members to put their hands up on the screen under the reactions there to come in. And oh, I see they're popping up right now. Maybe I'll start with Franz, since he's working with you to maybe pop in for his remarks before we get into the other questions.
I wanted to say that Oswald's economic calculation is very conservative, because if he makes cloud widening, he makes very little droplets, and it is known since 2 or 3 years that small droplets make H2O2, and H2O2 in the cloud, when the cloud surface is shined by sun, produces OH radicals, and these OH radicals deplete methane also. So he has an additional resource of methane depletion. And also, if he widens the cloud, he get a good reflection of the cloud. And this reflection makes much more UV above the cloud than if you have no cloud. And it is well known, the more UV you have in the atmosphere, the more OH radicals you produce. And this again increases his methane depletion rate.
Mhm, mhm.
Thanks,
Okay.
Franz. Can I just answer that very quickly? With regards to the scientific content you just said, I think that's fantastic news. Not complete news, but fantastic facts. However, with regards to the economic calculation, you see, the problem we have in economics is it's always way too cheap. So the problem is we don't want to hear that it's even cheaper, because the problem is, if we tell people that you can cool the climate with $2 billion, then they say, oh, you're crazy. That's impossible. It's way too little. So therefore, I'm aware that there's many things that will make it even more effective, but I just don't talk about it.
Interesting problem. Right. Well, let me move on to Mike McCracken. Mike, you have exchanged some emails with Oswald this past week about some of the issues. What is your current thinking?
Well, what I'd like to do is understand a little bit better this field test you're talking about, how you're going to make measurements, what you're going to do. And let me say that this idea that particles sink, that's not what happens in the lower atmosphere. They're carried around by the eddies. They're really too small to sink. So what's going to happen is you put out your particles, they'll have their reactions and deplete it. But because of the eddy motions and how things move around the atmosphere, those gaps are going to fill in awfully fast, I would think. I don't see why they wouldn't. And so, and the air is also moving along with the wind. And so I have a real question about how you're going to figure out what's really happening in the atmosphere, how you're going to take measurements about in the atmosphere that show that it's working.
Oh, Mike, you hit our weak point right away. The problem is, in fact, that MRV in a space of 7,000 cubic kilometers, only one dimension now, times 100 kilometers times 2,000 meters, is virtually impossible. There's no way that you can measure that in space. It's just, the answer is very simple. We are not and will not be able to measure this. And that doesn't mean that it's not working. The only thing is that we can't really put a measurement device into space and say, oh, look, we just oxidated 276 tons of methane. That's not going to work. But still it works, and we will do it the other way around. We will find a way to establish if at certain conditions ISA is dispersed, then we assume that so and so much methane is destroyed. And we will calculate that from lab experiments and from field tests and from all the different aspects of science, which will give us more and more information, and we will get better and better at it. But we will never really be able to measure directly what happens in these huge spaces. Now, the field test will give us a very, very important parameter, and that is more information about what we call atmospheric residence time or duration, right? Because once we can do the field test, we will be able to find out better how long do the particles stay. We will not ever know exactly, but we will have good average values, which will help us in calculating the effect. But coming back to the first answer, you are right. That's a weak point. That's a weak point actually with all geoengineering methods, that MRV is very different.
Very good.
Well,
Very
I
good.
guess I'd say that, one of my suggestions was to try and just do it in some sort of large enclosed space. The methane's going to be moving around in it. And if you have some sort of you know, if you had a sports arena that was closed, for example, and did methane in it, I mean, I imagine you could figure out how it could go, and it would go down. So that might be a way. The other thing that exists now is a methane satellite, and it's designed to look for, you know, methane coming out in sort of plumes from different places. You know, I guess it's conceivable that if you were to really concentrate your stuff in some place, it might be that under the satellite you could see something. I don't know, but that is a remote instrument or something that you know, maybe you find a highly concentrated area and try and, you know, do a cross track of a plume from there or something like that, and see if that might do something, if it's really going to do 10,000. And I'm not sure how you're going to know how are you going to figure out the lifetime of the aerosol?
Mm-hmm.
I mean, it's going to scatter widely.
It is certainly going to scatter widely. And we do not think that it will be possible to see this from satellites, even though the measurements do improve every month. You get news that they have a new satellite and it's improving again. And now they can actually see single sources. One big problem is you can't really see much over the ocean, and we will be over the ocean. The satellite pictures over the ocean are very much worse than over land. But even though, I still think that the dilution is so weak that you will not be able to see anything from a satellite. You do see sources, of course, because there the concentration is very high of methane. But the difference between 1.9 ppm and maybe 1.7 ppm is so little. I can't believe that you can see that from a satellite. I think your other idea is fantastic. I really like your idea with the big lab, and we are currently making lab tests with our room as a reactor, which is probably the largest reactor that has ever been used, and that works quite well. And with a stadium,
well, there is an international program that is set up to try and verify what country emissions are by using various remote kinds of tools. Sometimes they fly instruments in a plane, sometimes they use satellite stuff. One of the international scientists who's leading the effort is a sort of tennis partner of mine sometimes, but it might be worth asking them, because they do try and in some cases, go over cities, go over various things and see what they can see on plumes, and they find a lot of methane coming out, but they get pretty high resolution and have thought through things pretty well. So,
very good, very good. Well, let's
it would be great.
Or you could do in Switzerland. Why don't you do airflow through a tunnel or something? Measure it coming in at one concentration, have some aerosol in there, and come out the other end or something. Well, I guess there's no UV in the tunnel. That's the problem. Or something.
Well, let me suggest an offline conversation. I think, Mike, you may be able to offer some really interesting suggestions to the team there in Oswald's company. We have a number of other hands up, and let's start with Daniel Keith, and then move on to Doug, Ron, and Robert. Daniel? You're on mute, Daniel. Okay.
Sorry about that. Yeah.
Oh, there you are. All right.
Okay, can you hear me? Yeah.
Yes.
A quick question for Franz first. He mentioned H2O2 is produced. Is that right? So hydrogen peroxide.
Yes. Yes.
When small droplets of, is it particularly what droplets? Just seawater, or any droplets are really small produces that, or
what? Droplets, small droplets you see in the clouds, which are produced by condensation, you know.
Mm-hmm.
So literally the hydrogen peroxide is naturally produced by tiny particles.
only from water and oxygen outside. And the interesting thing is that the droplet surface is surrounded by positive high H3O ions, and the interior of the droplet is filled with OH minus ions. And there you have a big electric difference between them of 10 exponent 7 volts per centimeter. And oxygen diffunds into the droplets and becomes reduced by the interior OH minus, and this produces these H2O2 hydrogen peroxide, which is, and the smaller the droplets are, the higher the concentration of H2O2.
Okay.
And this H2O2 is unstable in daylight. It goes to OH radicals.
Right, and that's the thing.
Now let's take that very technical discussion offline, Daniel. Get in touch with
okay.
It was just a very significant one, because obviously I've been involved in marine cloud brightening groups as well, and that's really significant for both technologies, really, because that's another route to methane depletion from the same sort of
very short intervention here. Since 14 years or longer, Stephen Salter tried with nozzles to make small droplets for cloud whitening. But until now, the nozzle technique failed. It hasn't found a way how to produce such droplets. And so, big congratulations that Oswald can produce these small particles, 0.35 nanometers, not nanometers, micrometers. That's just the right dimension to make good white clouds.
Interesting. Yes.
Yeah.
Okay.
Okay. I went to. Can I just make one more?
Very quickly. We want to give others a chance. Please
Sure.
go ahead.
I'd say non-technically. I've just released a song which is about marine cloud brightening and direct cooling, and also brightening clouds in other ways. So it's just come out on Spotify, and it's called Fire from Ice. So I will stick the link if you want to have a listen to it. It's finally come. Yeah, Ron. I sent Ron's very talented daughter a previous a few months ago, but she's too busy to. Well, she's got brilliant sing. Anyway, I'll put the link to that in the chat.
Excellent. That'll be great for us to follow up on that issue. Let's go on to Doug.
All right, can you hear me okay?
Yes.
All right. Good to see you, Oswald. Last time we talked, you were deliberating over drilling rigs, abandoned drilling rigs or obsolete drilling rigs. You could probably get for a song. I have an idea that I'd like to pursue what Mike suggested, but depends on your answer. Just walk us through sort of the thought process of going from a drilling rig and all of the pros and cons to the drones and those pros and cons, and then that might trigger a comment or question, if you would.
Yeah, that's a good one. That was actually caused by a very frustrating experience. And that was, I was talking to a professor here for particles, and particles, let's call him a particle professor. And he said that what we are doing will not work, and he won't support it, because he said with those towers, which we planned 400 meters high, we would just scratch the surface of the atmosphere. And methane goes up to 17 kilometers. And with those towers, we are 400 meters. We would basically reach very, very little air room. And then he said, well, you have to imagine that the air is packed in packets, let's say of 1 cubic meter. Imagine that all air is packed in packets. And then you have to reach as many packets as possible with your tower, right? Now, you have the wind blowing over the tower, and of course, the wind will bring packets one after the other. So you have that wind speed. That's how many packets you get. But that's very, very little, very few packets. And then they travel, the packets travel, and then let's hope that your stuff will deplete all the methane inside that one packet. Okay, all done. But the number of packets is too low, right? Because once the packet is depleted, it's depleted. And then
But,
the stuff...
but the packets mix all up. Air mixes completely. I don't know why you're thinking of, it's not like in a balloon.
Yeah, I know. But he used that picture to make his point, right? And of course, he said, yes, there is, of course, interchange between the packets. But to make his point, he said, imagine that there were these packets, right? And then he said, then he said that you're way too low down there and you will not reach enough air room, basically. Let the packets away. And then we thought, oh God, what a bummer. What can we do? And then we thought, okay, let's put that tower higher, take a plane, and then move the plane, right? Well, height is one thing. If you are 10 times higher, it will just remain airborne longer. Not 10 times, no. Not Mike, not 10 times, but yes, it will remain airborne longer, for sure. And the second thing is, if that plane moves, and these planes move with 200 meters per second, whereas your wind is only 5 meters per second on average, something like that, then you get many more of these air packets touched within 1 hour or 1 second or 1 unit of time. That was very convincing, right? So this is why we changed to the planes, because we want to get more air room. That's it.
Okay, very good.
So just to comment, maybe follow up on Mike's suggestion for testing. If you were to have a drilling rig, or in this case a drone, the thought I had going back to the ROC days was to develop a drone that would fly a grid pattern through your dispersal plume. So let's say you would fly on the leeward side of an island in a grid pattern and take air samples at various different elevations and altitudes and on this grid. You could probably do the same thing with a drone. I don't know, maybe that's too scientific, too bizarre, I don't know. But to fly a drone to do instead of using a satellite and take air samples, just an idea.
Mm-hmm.
Yes, drones are used quite often for methane measurement. That is, of course, a good idea.
Great. Next is Ron. Go ahead, Ron.
Okay, thank you, Dennis, and thank you, Oswald. It's great hearing from you. And you've been very, involved with HPAC for a long time. I absolutely hope that you're very successful with this, because it's something it is absolutely could be a very useful way to both cool and reduce GHG effectively, although it's it's being transformed into CO2, but it has a less impact. I have two. Well, one question I just I can't help as a sort of I can't help noticing that or thinking that your distinction between nature methods and non-nature methods is somewhat arbitrary in my view. I mean, all of the methods mimic nature in some way, mimic volcanoes, mimic, sea aerosols, mimic. I mean, they're all, it's in some ways they're all trying to enhance these natural processes, and I mean, the difference between MCB and SAI, or it's just a matter of degree, a matter of leverage, perhaps, but not really. I mean, if you're using these jet propelled drones to disperse your methane, I mean, that sounds just as geoengineering as any kind of SAI being similarly dispersed by jets in the troposphere. So that's just a comment. I mean, I know it's part of your sort of viewpoint, and maybe it's not that essential that we all agree on everything here. It certainly isn't, as long as we can, we all are very aware of the problem, which is we have to cool as fast as possible and reduce, remove, and as fast as possible to get things stabilized in the long run. So that's one point, and then the other one is, I'm just curious. I'm sure you can. I mean, I assume you considered this, but why not use point source? I mean, these very, very concentrated methane emissions from oil wells, and the bubbling up in the Arctic now, and the permafrost now. I mean, I know there are folks that are going around saying, well, if we could just even, in some cases, just set them on fire, you have the same effect. If it's very concentrated, and you can, then you convert it to CO2, you oxidize it. So it just seems, it's almost like, I mean, I get it, it's sort of like direct air capture for methane, but it seems like, why don't we first tackle the really concentrated sources? I mean, I'm just curious as to why you went toward the just trying to do it through the atmosphere, which, as folks have pointed out, presents a number of very challenging issues of both the measurement, how to do it, how to get it, and I thought the conversation with Robert and Mike and you, and I mean, I thought it was very interesting as well. And but anyway, if you could just answer those two questions, I'd appreciate it. Thank you.
Very good. Oswald.
Very short, very short. With comparison to SAI, I mean, I've expressed my opinion very often, but the main difference is, of course, not in the natural mimicry, but in the fact that SAI does not restore the old climate. SAI creates a new climate, and that is very, very principally different from the georestoration methods. And that's for me the main point. But you are right, we don't have to agree on all the different things, and that's just my opinion, and I've stated it often enough, and that is not going to change. However, with regards to the second question, what was the second question again?
Why not use point source? Why not go after point sources?
Point
more concentrated sources.
Please, Ron, go for point sources. Many people do it. I think it's a brilliant idea. But we want to cool the climate, and with point sources, you will not. You will do maybe something with, maybe you can find a nice business model where some oil companies pays you for it. But if you want to cool the climate, you have to do big things, right? Really large quantities. And that is not possible with point sources. You can maybe go for 0.00001 degree, right? That's what you can get with point sources. And there are millions of sources, millions. And I think the oil industry, which is a dying industry, will not even clean up their mess, right? They won't even do what is really, really easy to do, is to burn, as you say, the methane where it comes out. They won't even do that, right? So I'm very pessimistic about the hopeful global methane pledge. I hope that I'm wrong, but the global methane pledge, which has been signed by many, many countries, will not work, in my opinion. It will just not work, because this oil industry is a dying industry, and it will not invest. It will just try to get as much profit out of this as possible. And it's also very expensive to do this. It's just much easier. What we suggest is much cheaper than any point source. Unless you look at, for example, some samples like in Turkmenistan, where they do these really horrible things, where they blow out millions of tons of methane, which you could actually just sell, right? Okay, in that case, I think there's some chances to pick those fat hanging fruits from the tree. They will do that, yes.
Okay.
But that's about it.
Very good. Thank you, Oswald. Let's move on to Robert. Robert Tulip.
Thank you, Oswald. I think that the big problem that you're going to face is social license to operate. We've seen significant pushback against geoengineering, for example, at the United Nations Environment Assembly and in the recent California marine cloud brightening trial, and so the whole issue of advocacy and of finding support and changing people's minds about the moral hazard concern are really significant roadblocks in the way. I put in the chat the link to the thesis proposal from the UK Advanced Research and Invention Agency. And I think that I'd encourage you to have a look at that document and consider the potential for work with the UK. But I think that this problem of permitting that was raised earlier is likely to be a major problem, and it raises again this issue of point sourcing, because the thing is that what you need to do is to prove, this is my opinion, is to prove a technology is to develop an incremental path towards field deployment, and that means proving that something is safe and effective in a very limited context before going into the open environment.
Comments?
Thanks, Robert. Can I answer that directly?
Yes.
We are very well aware of the social license issue. However, we think that time is working for us. The problem of global warming is increasing, and it is coming to a point where people really, really are looking for solutions. This has not been the case yet, but it is going in the right direction for our idea. It's not gone in the right direction for the globe. Unfortunately, it's going in the wrong direction, but that will lower the threshold for geoengineering ideas in general, not only ours. All geoengineering ideas will come into a risk assessment where you have to ask, what is more risky, not doing this or doing this? And since I'm an economist, I've learned that risk assessment always requires two scenarios, whereas most people make the mistake that they look at only one scenario. And that is, of course, then always easy to reject. And we are in close contact to youth organizations, and they are also changing their views because they see that it is not working what IPCC suggests, which is basically saying, well, let's do mitigation plus negative emissions. And it's entirely easy to prove that these methods will not solve the global warming problem. And increasingly, people understand that. And therefore, the alternatives will be, do you want to really risk not doing anything? And that question has to be answered by anybody who stops. For example, this wonderful experiment in San Francisco, which was stopped by the Catalina Council, which is really, I mean, that's just ridiculous that happens. And I think this will change, and this will have to change. Otherwise, we are going down the wrong way here.
Okay, thank you, Oswald. Rebecca has her hand up, and she's the one who hasn't had a chance. Oh, and then Robert, Chris, two that haven't had a chance to speak so far. Rebecca?
Thanks, Oswald and Franz. It was great to see your presentation, and I was waiting until Robbie had spoken because I thought he might raise a similar issue. And I'm so pleased to hear that you're thinking about social license and speaking with Operatio Arctis, or whichever the youth groups are. I'd just like to encourage you to put 1 or 2 slides about that in your presentation, because otherwise it makes it look as though it's in a vacuum and you haven't thought about it. And for example, when the trial got stopped in Washington or San Fran, wherever it was, with the spraying on the boat, Sarah Doherty said, oh, this is not unexpected, but it just goes to show that the smallest thing, like I loved what you said about a 10-minute field trial and that kind of thing, but if you could just paint a bit more of a picture about your seeking social license.
Well, as I said, I'm a very political animal myself. So I'm very conscious about political things, much more than I'm an engineer. And I'm not a chemist, and all these things I have to learn because that's a bit difficult for me. But political discussions are something I know quite well, and I'm very aware about geoengineering and the issues concerning it. However, for example, with Operatio Arctis, up to now, I cannot put them in any presentation or on our website, the fact that we work with them, because they didn't allow us yet to put anything on our website. And that's an issue we discussed with them since about 3 months. If we are allowed to say, actually present the fact that we do cooperate very well with them on our website. Can we put their logo? Can we say we love Operatio Arctis? Can we say that? No, that has to be discussed. And that's a big issue, right, in Operatio Arctis. So even that is difficult. Anything you do in this area is difficult, very difficult. Now, but we are a bit different than scientific groups. We are a company, and companies do things. Companies don't discuss all the time. They do things, and that's different. I'm not gonna say where that's gonna come out, but we will do this field test. It's not that we will discuss if a field test is a good thing. No, don't get me wrong. We will do this field test. Full stop.
And I think Rebecca's point was that to make people more aware of your efforts regarding social license, it would be good to put some slides in about your current work in that area. So let's see. We have Robert, Chris. You had your hand up a little earlier. Did you want to come in now?
I would. Yes, thank you. I'm going to just make a couple of very brief points. I thought that Robert Tulip's point I was unhappy about, because I think that something that, Oswald, I don't think you convey clearly enough is that what you are doing here is actually a form of greenhouse gas removal. Instead of removing carbon dioxide from the atmosphere, what you're doing is removing methane from the atmosphere, just a different greenhouse gas. And in that sense, it's quite different from the way that the word geoengineering has now, from its early stages 15 years ago, when it referred to both carbon dioxide removal and to solar radiation management. Today, geoengineering largely refers only to solar radiation management. And what you are doing, although you acknowledge that it does have some reflective activity as a side effect, it's principally a greenhouse gas removal project. Now, where it gets confusing for ordinary folk is that you are doing it by using a technology which looks very similar to stratospheric aerosol injection, because you are sending devices up into the sky to spread stuff. Okay. And that's why I think there is this confusion between the two, because it looks and sounds like SAI, but it actually isn't. And I would counsel you to try and convey that distinction more clearly. And I think you might find it easier, or the objections might be easier to deal with if you were to do that. And also, the other thing that you've got going for you here is that what you are distributing, what you are spreading out in the atmosphere in terms of ferric chloride is something that you can demonstrate from the science facts, that it is a fact, that it's up there by nature. I mean, you know, there's tons of this stuff gets thrown up into the sky every day from the Sahara. It's what keeps the Amazon green, you know, and so on. So is that not right? Okay,
no, that's not right.
Okay, fine. Well,
No,
that's
actually, that's Fe2O3 that's thrown up. Fe3O3 is not thrown out of it. It doesn't exist in
that's my. But in any event, I think that it's this kind of, what you've got here is a project which is kind of it's nominal. It is actually a greenhouse gas removal project, and it looks like a stratospheric aerosol injection project. And I think that penny dropped whilst you were talking for me. And I suspect it might be helpful for others if you dropped it for them.
It's not quite right, Robert, because iron salt aerosol has a major weather modification effect through albedo enhancement. There are significant albedo enhancement factors, and what you're alluding to is that there's this deluded public campaign that says we must not brighten the planet in any way because of the moral hazard. And that's where I think the fact that ISA does brighten the planet means that it will face exactly the same solar geoengineering moral hazard arguments as SAI and MCB.
Well, that's Oswald is shaking his head. I'll let him answer that. But the way that he's presenting it,
that's exactly the difference. You have to differentiate. MCB now has a very good reputation now. MCB is a word that has been accepted, really. Look at, mainly because of the activities in Australia, in Queensland. Now we have these ongoing experiment, and everybody's very happy about this. And that will change the perception for MCB, and it will be more and more accepted to actually spray sea salt into the air. So we are doing this at the present, and everybody is clapping. That's a fact. That's something that happens. It's not a project. It's something that happens since 2 years. So MCB is okay. Now, how do we draw the line? I draw the line exactly there. I say MCB is something that we do too. That's great. It's wonderful. It's a wonderful thing. But we are not going to 13,000 meters at height, and we are not changing the solar radiation. That is different. For us, that is the big difference. Of course, you may say that is opportunistic because, well, but that is exactly what we do. We are a company, so we defend our system. And we are opportunistic. Yes, we are. We will do this. And we think that SAI has been caught in an endless circle of discussion and will not get out of that circle ever. It will just remain there. And therefore, I want to get away from the SAI discussion, and I want to go to a discussion where we have friendly systems, nature-friendly systems, which don't master nature. We don't tell nature how to do it. Don't do that. But serve nature and use nature. It's a friendly, wonderful way to do these things. And it will be accepted. Don't worry about it. Like MCB, things change.
Thank you, Oswald. I'm sure that comment will open up a whole can of worms. But I wanted to have John McDonald be able to come in because we are running out of time. And John, you have a quick question? You're on mute, John. You need to unmute. John, you've got to unmute yourself.
Sorry, I love what you're doing, Oswald, because I'm a shareholder of AMR as well. But you, as others are saying, you need to tick all the boxes to head off any criticisms. And one detail, for example, is the fuel source for planes. If you could possibly do it with biofuels or ultimately batteries, although the payloads are pretty serious, that would be another possible criticism. Have you thought about that as an idea?
Oh, yeah, but at this stage, we don't have any alternative. And I think we have to realize that the climate change was caused by old industry. And we will need some old industry to actually remove the greenhouse gases. If we want to do that, we can't do it all with the wonderful, I love the new industry and the electricity and all that. However, it just doesn't have the power we need. We need this jet engine. We need this heat. This is very physical, and you can't do it with a drone, with an electric drone. You need a jet engine. You need fuel, a lot of power to disperse nanoparticles. It's not so easy. The technology is quite sophisticated, and we do need a jet engine, and therefore it will always be a jet, right? Nothing we can do.
Yes, I think similar analogy with using ships for MCB. I mean, they're out there now. I mean, that's they're using traditional fuel, although that's changed recently. So yes, we need to get it going and then perhaps transition if we can in the future.
That's possible. Yeah. Well, we had two hands left, and I see Robert came back in. But let's ask Mike to make a quick comment, and perhaps Robert has another quick one, and then I'll finish up with Franz, maybe putting the frosting on the cake. Mike?
Well, I guess first I'd say with respect to MCB, it isn't harmful to put sea salt in the air. Nobody disagrees with that. The problem is to get the cloud brightening, you have to get exactly the right amount, or you might do something different. And that means you have to have measurements right around where you're doing, and it's constantly changing as the weather changes. So the idea that it's sort of, that it will be effective as a large scale thing is really sort of up in the air. I'd still say. What I want to make sure I understand is so you're talking about bringing the methane down to pre-industrial level, I guess, is what you're doing. You know, what bothered me a little bit about your graph, I mean, your table of all the different things that you calculated is they're all rough numbers, and it didn't seem to come across that way. I mean, what I assume you're going to have to do is start, if you did it, you would go in and put some in and see what the response is, see how the concentration comes down somewhat, and you'd work toward this thing. But this number of 10,000 that you have per reaction is kind of, you know, I mean, that's a rough number or something, I assume. That doesn't count. And stuff. So I just, and the idea that you're going to also get cloud brightening, I just don't think is a realistic one to say, because once your particles in the cloud, the average lifetime of CCN in the atmosphere, that's the whole problem with marine cloud brightening, you know, is a day or two. Is it going to really persist? That means once it gets in a cloud, your stuff's going to probably come out pretty quickly. So you want it staying in the open air as much time as it can, I would think.
Okay.
Oh yeah. Can I answer quickly? The marine cloud brightening for us is a side effect, right? We don't even calculate any income from that or any cooling effect. We just say it might actually cause
in some places where it's the right number. I mean, yeah, I don't think it's worth making that argument. The iron into the ocean as not being harmful is a legitimate one, it seems.
Yep. Okay. Robert, Chris.
Sorry. Excuse me. I just wanted to make a quick reference to that long email correspondence or exchange we had during the week. First of all, I just want to thank Mike for your extraordinary patience and contribution to that. It's very, very valuable to have someone like you that cares and has the time and the inclination to help us all out on these things. So,
That's
so
my
thank you very
favorite.
much for that. And secondly, I just wanted to say that I think what you are doing, Oswald, is great. I don't have any issues with it, except my concern, which I put in the chat, just this simple question, that notwithstanding this email exchange, these messages, I am still really unclear about how quickly the surface temperature changes from the methane elimination happens. For me, timing is, the quantity is good. You can take out half a degree, fantastic. But half a degree in 20 years is not the same as half a degree in 100 years, because we are facing some very critical changes in the coming decades. So I have not yet got my head around this timing issue.
Yes.
Quick answer, we can't do it faster. Even if we would have all the money and all the technology ready, it will take 20 years. The technology we propose.
It's not about your technology, about how quickly you can roll it out. It's really about the climatic impacts and the climatic effects. I don't really understand the climate.
Robert, you misunderstood me. I'm not talking about the climatic impact, because that's only after we have actually lowered the methane. And it takes us 20 years to lower the methane. So then, after that, it starts with the climatic impact, right?
But you're counting the new source of methane that keeps coming in all the time, right?
Yep, of course.
Yeah.
Yes.
Great. Well, we're just about to close, so I would ask Franz if you had a short intervention to wrap things up for us today.
I had an answer to Ron Bainman's question. He sorry, lost the red thing, but the point, yeah, now I know point source is you can't use this technology for point sources because the concentration is so high, and you should make a very dense aerosol of this iron, and this would put back the sunshine you need for chlorine production. Another problem is if you have such concentrated methane resources, the problem is that you also, with the chlorine radicals, you make chlorinated hydrocarbons. That's not the thing. They disturb the ozone layer. That wouldn't be okay. Then
I wasn't suggesting that technology, but yeah, thank you, Franz.
Yeah. And the next is what Oswald said. He said Sahara dust is not that what we want and what we do, but it is exactly the same. Why? Because in the atmosphere over the Atlantic, where the Sahara dust flows, you have around about 600 to 800 ppt HCl. And this HCl reacts with the surface of the iron particles of the Saharan dust. You know, Saharan dust is red. So you have iron. And this makes a small coat of iron 3 chloride on the Saharan dust particles. And these iron 3 chloride produce the chlorine radicals which deplete methane. And this has been described in a paper from last year from Martin von Herpen and others.
Right.
They measured these things. And to Mike McCracken, I would say, and Robert Chris, that the effect of cloud widening by aerosols acts very fast. You can see it from the ship tracks, from the cloud ship tracks on the Pacific, when they, but it works only where you have clouds. You make them whiter, and this makes the ship tracks.
Okay.
Yeah, I agree. And of course, fast. The problem is how long lasting it is and compared to everything else. But yeah.
Ship tracks last long.
All right. Well, thank you so much, Oswald, and for the enhanced interactions of Franz and your other colleagues. In closing, I would reinforce Ron's point that I think we all must wish that your efforts will be successful. And clearly, a number of our other HPAC members have very interesting suggestions for your work. And I look forward to their continuing to be in touch with you to enhance the success of your efforts. So we'll be following your work with great interest, and I hope we'll be able to get updates from you quite frequently as we move into the future. So on behalf of us all, thank you, Oswald, thank you, Franz, and we look forward to a successful introduction of your technology in the near future. Thanks.
Thanks a lot.
Thanks,
Great
everybody.
to be here.
Thank
Thank you,
you.
everybody.